After discussing atoms and recognizing that they are actually not the smallest particles of matter, but in fact the fundamental particles comprise all of the constituent pieces of matter, fundamental particles are very small and very numerous, but they are only controlled by four fundamental universal forces. The four fundamental forces are the current theory of how everything in the universe works. And so the fundamental particles are very small, but the rules that they follow are relatively straightforward. Fundamental forces. The first of which is called the strong nuclear force. Strong nuclear force is very strong. And the reason for that, of course, is if we think about the nucleus, as I discussed, if the football stadium is the atom and the nucleus is in the center, right? The nucleus is the size of a tennis ball inside the center. If I then take the nucleus and I think about the nucleus as being a large collection of protons and neutrons, many protons contained within that tiny dense center of the atom is not something that normally would be a situation that would stick around, because, as you know, like charges repel. And so the opposition of positive to positive driving these protons apart would naturally make matter and the nucleus and ultimately matter impossible to form. And the strong nuclear force is the way that matter overcomes that. The strong nuclear force has an extremely short range, but is remarkably strong. And what it is an attraction between quarks. And so within the nucleus, as long as we are at 10 to the negative 15th meters or less, protons and neutrons are actually locked together with a very, 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 very strong interaction called the strong nuclear force. Since this is a fundamental force, this is something that is universal and natural. What is important to recognize is that it is limited in terms of range. So once these protons get beyond the scope of the nucleus, which is what's accomplished in a nuclear bomb, we actually push these protons just beyond the boundary of the nucleus, then the protons are driven apart, right? That's the mushroom cloud that you all recognize as a nuclear explosion. So you can imagine that the energy necessary to hold protons into that tiny tennis ball that then comprises the fundamental mass of the nucleus must be remarkably strong. In order to do this, there are two bosons that act within the strong nuclear force, within the nucleus, in order to transmit the information between protons and neutrons, and of course neutrons and neutrons, in order to hold them together. The first of which are called gluons, and they actually transmit what's called the color force. The color force would be the characteristic force that is actually holding protons together, right? So the quarks within themselves. And then, of course, pions are a secondary characteristic that would act outside of the individual quark, or outside of the individual protons and neutrons, but within the nucleus, acting to hold the protons and neutrons together. And so strong nuclear force has two force carriers doing similar jobs at a remarkably strong strength. The strong nuclear force, of course, exists to overcome the electromagnetic force. And the electromagnetic force is the force that you're probably most familiar with, right? Which is the attraction or repulsion of charged particles. Now, charges, of course, exist in the nucleus as protons repelling each other, but they also exist across the nucleus into the electron cloud as protons attracting electrons. And so the electromagnetic force is the force responsible for that interaction. And as you see, this one is the first indication of the fact that force can both be attractive and repulsive, right? And if we go back and investigate, that is actually true for the strong nuclear force as well. It is an attractive force that holds these particles together, but once they get too close together, it actually becomes strongly repulsive as well. That's what determines the size of a particular proton, the size of a particular neutron, and ultimately the size of the nucleus. So how strong it is holding together determines the ultimate size. Electromagnetic then, of course, determines the ultimate size of the atom, which includes the electron cloud, by attracting electrons to the nucleus. Now, if we think about the discussion that I made in terms of the electrons moving around within the electron cloud at a remarkable speed, almost near the speed of light. In order for a proton to send information to an electron and actually get there in a meaningful time before the electron goes away, that means that this particle, the boson of the electromagnetic force, must be the fastest particle known, which of course are photons. Photons are particles of light, and they are the only massless particle on our fundamental particles list. Since they are massless, they are able to move at the speed of light, which is the universal speed limit. It is the fastest possible moving particle that exists. So that makes it capable of communicating with electrons and transmitting the electromagnetic force, which ultimately attracts the electrons to the protons, which then creates the nucleus, or creates the atom, excuse me. But then, of course, a consequence of the electromagnetic force is that the protons repel, which is therefore the required strong nuclear force to balance it out. So you can imagine that a nucleus is a delicate balance between these two forces working against each other. Beyond those two is the much more complicated to understand force known as gravity. Gravity in this sense is not what you would think of it here on Earth. Gravity as a fundamental force to the universe would be the attraction between fundamental particles. So ultimately, the gravitational force, or the fundamental force of gravity, determines the mass of any given particle, right? Any given fundamental particle. And so gravity has been the most studied recently, and certainly one of the more difficult to understand, because this particular force is an attraction only, and up until 2012, the boson wasn't even known. It took the creation of the Large Hadron Collider, which is a gigantic electromagnet built outside of Geneva, Switzerland, underground to accelerate particles, smash them together, and study them, in order to determine what is now known as the Higgs boson. This is also referred to as a graviton. This Higgs boson is a messenger particle that transmits the gravitational force and creates the attraction between all particles. And if you think about it in terms of a universal, gravity being an attraction is how matter is formed. If we think back to the nucleus, right? Remember that the nucleus, the strong nuclear force, has a short range. Well, that short range limits the creation of matter. So if I had two protons that are far enough away, the electromagnetic is going to push them apart, and so matter would never form. Gravity creates the conditions necessary for the strong nuclear force to take over by pulling fundamental particles into large masses that ultimately push protons together to create nuclei. Those large mass collections, of course, are stars. And so stars are where gravity pulls the particles close enough together. Once they get there, the strong nuclear force holds them together as a resistance to the electromagnetic repulsion of the protons. Once the protons and neutrons are formed in the nucleus, then through electromagnetism they attract electrons. The electrons become trapped within a particular volume known as the electron cloud, and bada bing, you have an atom. the fourth fundamental force is one that is still being studied and relatively difficult to explain, because the weak nuclear force is another force that forms within the nucleus and carries two bosons that are they are called the W and Z bosons. They do not have a fancy name, they just have a letter designation. This is partly because the weak nuclear force is the least understood of the four fundamental forces. We know it exists, and the reason why we know it exists is because of two things. First of all, the stars that we've talked about give off energy, right? We know that because our sun gives off lots of energy. That energy comes from an entirely different reaction than we typically experience on Earth. That reaction is a nuclear reaction where the actual strong force is being affected within the system. Well, since gravity is pulling the matter together, electromagnetism is pushing them apart, but not changing them once it's stuck in the strong nuclear force. The only way for an atom to change its state so that it can give off energy is through the weak nuclear force. And so these bosons, these messenger particles, go into quarks and actually tell them to change roles. And so if you think about a proton being two ups and a down, two up quarks and a down quark, the weak nuclear force will send a W boson into a proton and change one of the up quarks to a down quark. This happens what we would call naturally, right? Fundamentally based on this weak interaction. But when this turns into that, the matter itself has changed, right? A down quark now exists within a collection of up and down, and so now we've gone from a proton to a neutron. Well, changing from a proton to a neutron imbalances the electromagnetic repulsion of an atom by either adding or subtracting protons to the system, which can then cause the electromagnetic force to drive the particles outside of the range of the strong nuclear force, which can ultimately cause a change in the atom itself. And so the weak nuclear force is responsible for fission and fusion, which are stars, and they are also responsible for radioactivity, which you're familiar with here on Earth if you know anything about cancer treatment with radioactivity or radon treatment at your house, where radioactive particles are being formed underneath the ground and then move as a gas through your house. And so the weak nuclear force is still being studied and certainly very interesting, but that's where that the fundamental particle known as a neutrino that I mentioned in the previous video becomes relevant and is currently being studied. These four forces create the patterns to all matter, which drives all of the universe.